Hello everyone, welcome back to this channel. Let's continue our course Intro to Machine Learning. As of now, we have completed how models work, basic data exploration, your first machine learning model, and model validation. Let me give you a small recap, then we will start underfitting and overfitting. Okay, so let me first open this one. We took a data set, a housing pricing data set. No, here the data set is home data for ML course, and then we then we created a data frame using this data set. Then we selected the output, the input, then we built the model, we fit the model, and after that we also evaluated the model using uh, mean absolute error. Okay, so first we have downloaded the data set, then we converted it into a data frame, then we selected the output feature, then we selected the input features, then we downloaded decision tree algorithm, later we fit the model and we predicted from the model, and after that we mm, we evaluated the model using mean absolute error. So as of now, we have done all these things. Now we are going to study underfitting and overfitting. Okay. As usual, first I will read, then we will do the exercise. So at the end of this step, you will understand the concept of underfitting and overfitting, and you will be able to apply these ideas to make your models more accurate. Okay. So experimenting with different models. We have just used decision tree, but now we will see other models. Now that you have a reliable way to measure model accuracy, you can experiment with alternative models because you have seen the decision tree model was not performing that well. Okay, so we can check other models also and see which one gives the best predictions. But what alternatives do you have for models? You can see in this scikit-learn's documentation that the decision tree model has many options, more than you will want or need for a long time. The most important option determine the tree's depth. The tree's depth. Depth means how many splits you will make. Okay. The first lesson we understood this one, that the tree's depth is a measure of how many splits it make before coming to a prediction. This is a shallow tree because only two splits. Okay. But in reality, it may have more than two splits. It may have many number of splits. Too much splits also can be a problem. Too small number of splits also can be a problem. So it's not uncommon for a tree to have 10 splits between the top level and a leaf. It depends on how many criteria you have, how many input features you have. So depending on that, your tree may have many number of splits. That is known as the depth of a tree. And by changing all these things, you can improve the accuracy. Okay, as the tree gets deeper, the data set gets sliced up into leaves with fewer houses. If you had only one split, it divides the data into two groups. One split, yes or no, two groups. Okay, if each group is split again, then it will give you four groups: first, second, third, fourth, depending on two split. Okay, so splitting each of those again means, see, if you split this one, it will give two, it will give two, it will give two, it will give two. So it will be 20. So if you keep doubling the number of groups by adding more splits at each level, we will have 2 to the power 10 groups of houses by the time we get to the 10th level. Right? So 1024. 2 to the power 10 equals to 1024 leaves. So when we divide the houses among many leaves, we also have fewer houses in each leaf. Leaves with very few houses will make predictions that are quite close to those homes' actual values. If you divide your total 10,000 houses into many parts, that means every part will have fewer houses and some part will may have very few houses. So what will happen when you make the prediction? They will give you a very good prediction. They will give you a good value, but they may be unreliable predictions because for new data it may not match. So it may give you a very good result while training. But in a real scenario, when you will take any real data, any new value, it may not match. Okay, so this is known as overfitting because you are trying to understand the pattern so well that you are actually missing out from the reality. You get my point? This phenomena is known as overfitting, where a model matches the training data almost perfectly because you are dividing it in so many points, in so many fewer leaps that your criteria is matching exactly. So what is happening in during the modeling, during the training, it is giving you a very good performance. But real time testing, it will give a very poor result. On the flip side, if we make our tree very shallow, shallow, maybe these two. So what will happen? So you will not get a good result during the training. Whenever you will try to fit, it will not give you a good result because you are actually not splitting at all. So it will perform very poor during training. This is known as underfitting. So the main difference between overfitting and underfitting is that during overfitting, your model trains extremely well in training but not during testing. And in case of underfitting, your model is not performing in training period as well. Okay, so very shallow tree, less fit will give you underfitting, very depth tree will give you overfitting. So since we care about accuracy on new data which we estimate from our validation data, we want to find the sweet spot between underfitting and overfitting. As I said, you have to take the midway so that you don't underfit or you don't overfit. Okay. Now see, this is the mean absolute error. This is tree depth. Tree depth is increasing, mean absolute error is increasing this side. So here both of them, see, this is the error. The error is high during training and the error is high for validation. Perfect. Both of them are getting reduced. Mean absolute error getting reduced. Tree depth increasing. After a certain period, after this period, see, during training, mean absolute error is getting reduced. So it is nice. But the problem is with validation. Validation, it is not getting reduced anymore. Even, in fact, it has started increasing. So mean absolute error is getting reduced for training, but not for validation, as that tree depth is increasing. Okay, so you have to stop your training here so that you don't you don't get underfit or you don't your model doesn't become overfitting. Okay, now there are a few alternatives for controlling the tree depth. How can I control? There are some alternatives and many allow for some routes so that tree to have greater depth than other routes. Okay, but the max leaf nodes argument provides a very sensible way to control overfitting versus underfitting. The more leaves we allow the model to make, the more we move from the underfitting area. We can use a utility function to help compare MA scores from different values for max leaf nodes. See here. Mean absolute error, we studied in our last class. This calculates the error from the prediction. Decision tree regressor, we know from our first day. Now you have written a function get underscore MA. Here you are passing max leaf nodes. That means you are giving a value for maximum leaf nodes so that it doesn't get overfit. You are giving the training where the input for the training, validation, output, validation output. No problem. Now you are creating an object of decision tree regressor, maximum leaf nodes equal to what you are passing from here. That will be the max leaf nodes. This is a parameter within decision tree regressor and it will take a value you pass while calling this get underscore MAE function and where you can just inform that how many maximum leaf nodes you want. Okay, and random state equal to 0. Random state equal to 0 means you know. Now model dot fit equals to train x train y. So you are fitting the model. Prediction. So model dot predict validation x. Now you are calculating the error. So actual value and the prediction value. All these things you have done, and now you are returning the image. So all these steps you have written inside a function get underscore MAE, which will be called later on. It will be more clear slowly. Now that the data is loaded in train X, val X, train Y, validation Y using the code you have already seen. So the hidden code. See the complete code. Import pandas. This is the file path. You are converting it into data frame. Now you are deleting some missing rows. Now Y, that is the output feature, input features. Now you are calling train test split. You are splitting this into two parts. Now you are comparing MAE with differing values of max leaf nodes. See here, you are giving the max leaf nodes. Now you want to check which one will be more suitable. So what you can do, you can take 4 or 5 random numbers and then you can check which one is performing better. For which leaf node, it will not underfit, it will not overfit. Perfect. Now see, 5, 50, 500, 5000 for values. Max leaf nodes, for max leaf nodes, in this number, you are just starting a for loop and for every number, you call the getME function. So first it will take 5, it will call this function. So max leaf nodes will be 5, train X you know, val X you know, train Y you know, val Y you know. If the, here it will be set as 5, random state you know, it will be fit, it will give you the error. So for 5 leaf nodes, you will get some error. Perfect, you paint it. See. Okay. Next, in the next for loop, it will take 50. Same way, it will go here. Max leaf nodes will be set to 50. All these things will run and then it will give you some. So for max leaf nodes, this is the output. Same way you are doing for 500, you are doing for 5000. Okay. Now after you do all these things, you can check which one has the minimum mean absolute error 24,000. So that's why they are saying 500 is optimal. Okay. So what you are doing here after you have evaluated your model, you can check that how I can improve my model. Simply, how can I improve? How can I stop overfitting and underfitting? Underfitting means it is performing poor in both scenarios. And overfitting means it is performing good during training because it has uh, kind of rehearsed the pattern. It has just it didn't understand the real thing, but it has just remembered everything like that. So that is why it is performing good in training but not during validation. So to avoid both of them, we have to find for which leaf nodes the minimum is the error. So once you find that, you can take this as your optimal algorithm. Okay, and for that you have to run this for loop. So the takeaway is overfitting. You know, underfitting, I have told you, we use validation data which is not used in model training. Let's try to, please let's try, us try candidate models and keep the best one. Okay, now let's do it. You have built your first model. Now it's time to optimize the size of the tree to make better predictions. Run this cell to set up your coding environment. Let's recap the whole thing. You have imported pandas, mean absolute error, train test split, decision tree regressor. This is the file path, and you have converted into a data frame. Y is the output feature. These are the input features. You have splitted the data into training data into validation data using this method. Then we have specified the model, decision tree, and fitted the model. All these things are done. Perfect. Now your exercise, you could write the getME function yourself, but they have written it. You can write it in yourself also. The same thing we did here. Okay, let's just show you. Where is the getME function? This one, simply same function. Okay, now compare different sizes. Write a loop that uses following values to find the exact ideal size. Okay, so now we can write the loop. Now to write the loop, let me just copy this. This is the loop. So I can write for max leaf nodes in, write this one. For max leaf nodes in this candidate max leaf nodes, that means it will take 5, 25, 50 in every loop. Okay. So in the first loop, it will take 5. Get AME function is called. So it will come here. It will be 5 and all these things you have set up before. Okay. Now you have to write scores. Oh, I'm so sorry. What happened? Scores equal to, sorry, scores. Here we can write notes equal to mm, MAE. Okay, now first you have to initialize the dictionary, empty dictionary. Now let me, oh no, here it is not given. So we have to write best tree size. Here I have started a for loop. I am taking all the values. I am passing it to get MAE function. I am getting the MAE and I am taking this MAE. Now what is the best value? Best value, which one will be the best value? Where the MAE is the less, the minimum. Absolute error is the minimum. Will give you the best solution. So you have to find the minimum value. So how can I write this? Just write this function. Write this function mean scores comma key equal to scores dot get. So it will give you for which number, for which leaf node number, the error is the minimum. Okay, now let me first run this. Uh, there are some errors like for max leaf nodes in candidate max leaf nodes, my MAE equals to okay, this is my MAE. So I have to write here my underscore MAE. Whatever it is here, the absolute error that is stored in this dictionary. Let me show you the scores, then it will be more clear to you. Hmm, print scores. See, this is a dictionary. I first initialized it as an empty. Now for 5, this is the error. For value 25, this is the error. For value 50, this is the error. So you have got the dictionary. Now from here you can see for which value the error is the minimum. But or you can use this line of code. So it will give you the minimum of this value. So the minimum of scores, you will get the key value. This is the key. So 50, 100 to 50. See which one is has the minimum. 35, 29, 27, 27, 27, 500. So the minimum is 29. Which one is the minimum? 27, 27, 282, 27, 893. So 100 is the best, I think. Now if you print best tree size, it will give you the key value 100. Okay. So it is just checking which score is the minimum and corresponding key is retrieved here and you are printing this. Perfect. So this way you are just uh, starting a loop, taking all the values, passing it to getMAE function. You are getting some error in return and you are storing them into a dictionary and then you are taking the minimum value from the dictionary and corresponding key is printed. Okay. Now you can see their solution also. What happened? I don't know what happens sometimes. You can check by yourself. Or if you know what is dictionary comprehension, then also you can do the whole thing in a single line. Okay. Or you can do it step by step as you feel comfortable. Now fit model using all data. You know the best tree size 100. If you are going to deploy this model in practice, you would make it even more accurate by using all of the data and keeping that tree size. That is, you don't need to hold out the validation data now that you have made all your modeling decisions. Okay, fine. Now fill in an argument to make optimal size and uncomment. Final model dot fit. Final model equal to, you have to pass max leaf nodes or node. Uh, Nodes, you have to be very careful about this. So max leaf nodes equal to, what is the max leaf nodes here? 100. That is the best tree size. So just paste it. Okay. And you have to now fit the model. So for fitting, you need two things: input and output. What is the input here? Train X. What is the output? Train Y. So you just copy this, write it by yourself. Don't copy like me. Okay. Why is it not running? I don't know. That's what happens. Okay, let me. See, this is entry regressor, maximum leaf nodes 100. Okay, this is perfect. You can see the solution. Now you have tuned this model, improved your result. But we are still using disease entry models which are not very sophisticated by modern machine learning standard. That is okay. That you should not think right now. But if you want now also after this, you add one cell and I'm giving you the task. You do it by yourself. You take the mean absolute value. Sorry, mean absolute error. You take this one. The mean absolute error. What is the function? I mean to say you take the mean absolute error function, this one, and you try to calculate the MAE for the leaves when the leaf size is 100. Okay. So you explicitly mention the max leaf nodes as 100 and you calculate the MAE. Okay. You do it all by yourself. Just try to write all the things you have learned as of now. Just take the data set, convert it into a data frame. You take the training value, testing value by using train test split, then take the output y value. Sorry, before that you have to take the output features. You have to take the input features, and then take the decision tree algorithm. Explicitly mention the leaf size as 100, and then you fit the model. You evaluate the model, and you print your minimum accuracy value. Sorry, minimum absolute error. Okay. So you do it by yourself. All the other things have been done. So in our next class, we will understand random forest. Till then, bye. Happy learning.